We focus now on the second of these integrals, this one. The problem of this one is, of course, at 0. It is problematic because the argument of the exponential is 1 over x, that's one thing. And the other one is because you have a power of x, which can be negative, because there's no constraint on the value of p, right? Of course, there's no problem at the other limit, a, right? The functions behave properly near a. So this is an integral, an improper integral of the second kind because of this 0, right? Because it's the divergent of the function at 0. So the first thing we're going to do is to make a change of variable, right? And we transform this integral by changing to the variable 1 over t. X is equal to 1 over t, right? Which means dx is minus 1 over t squared dt, right? Okay, and well, you have this minus here, okay? Then you have the limit when x is equal to 0, t is infinity, right? Plus infinity, because we are in the positive side. Then the other limit is 1 over a, of course. And then you have et x2 minus p, t2 minus p, t2 minus p dt over t squared. All right? And this minus, with this minus we interchange the limits, so we have the integral from 1 over a to infinity of et, and then you have dt over t up to the p plus 2. Right? So this is the integral we have to deal with, right? Now, if you look at this integral here, of course there's a power which, if p is positive, or, well, if p plus 2 is a positive number, then when t goes to infinity, this goes to 0, which is good. However, it is multiplied by an exponential, and exponential always dominate powers. So the behavior of this integral is going to be a function that goes to infinity. So the suspicion here is that this integral is not convergent. But if we want to prove it, we need to find a function with which we can compare. But it is easy to do that, because all we're going to do is to find another exponential, another growing exponential that, however, goes to infinity slower than this function here. And for that, we just need to take, for instance, the exponential with half the argument, right? If we divide that by this function here, et t minus p minus 2, right? What we have is this function, is the limit when t goes to infinity, and then t half minus t is minus t half, so we have minus t half, right? And then you have t to p plus 2. Well, again, it doesn't matter what the power of this function is, this limit is always 0 because this exponential goes to 0 when t goes to infinity. So now we need to see what happens with these integrals, but we know what happens with this integral here. The integral from 0 to infinity, well, actually from any constant c to infinity of et half is, of course, infinity. Well, the primitive of this is 1/2 this exponential, and when you take the limit when the argument goes to infinity, goes to infinity. So this integral diverges. The limit of this is 0, and the integral here diverges. Then by the limit comparison test, the integral of this one diverges too. So this integral is divergent.